Oh, okay. Okay. So actually, I put the first homework assignment on the Blackboard. But this homework is a very simple homework, which means that this homework you are requested to study the configuration of NVIDIA GPU architectures. So actually, NVIDIA changed their GPU architecture from it to recently they announced the Hopper, but I think recently they also launched the new ITX 4000 series Hopper architecture. But in the assignment, you are requested to study until the Ampere architecture. So actually, they changed their GPU configurations and their GPU architectures. So actually, we are learning about the configuration of streaming multiprocessor. So actually, which means that the streaming multiprocessor is similar to the core of CPUs. So I hope you study the different configurations of NVIDIA GPU architectures. Okay, so actually, after learning about the SM, the streaming multiprocessor, and memory hierarchy of GPU, then we will also cover the GPU simulator called GPU sim. Then the GPU sim is the architectural simulator. So that is the software, but the software emulates the behavior of processors. It's a cycle accurate simulator. So in order to use the architectural simulator, we need to change the configuration, such as the size of register file or size of around cache. Also, we can change some configurations like the number of SMs or something like that. So, in order to use the architectural simulator, it is also required to understand the meaning of some configuration values, configuration parameters. So that's why I provide some very simple assignment. So you can just search for some GPU white papers, or you can also search. You can also get some information from Wikipedia. Okay, so just write just find some configurations, and then also study the change of architectures in the NVIDIA GPU generation. Okay. So in the previous class, we covered some brief architecture of the NVIDIA GPU streaming multiprocessor. So actually, as I mentioned, the streaming multiprocessor is similar to the core of CPU. Then I also mentioned that this streaming multiprocessor execute the works. Okay, and then so as I mentioned, NVIDIA also changed their GPU architectures from it to actually here Volta. So so they changed some configurations, like the separated work schedulers or something like that. So you can find some information from the NVIDIA GPU architecture white papers. Okay, so we are learning about the SIMT and SIMD. Okay, so as I mentioned, the streaming multiprocessor execute warp. The warp means the group of thread. Okay, so it means that actually warp group the So in the NVIDIA GPU, also it's the same to the AMD GPU. The warp is all the way from AMD GPU. The warp is the group of thread. Okay, the warp group started to thread. Okay, and then it started to thread execute the same instruction. So you know, even though the instructions are the same, but it's a different thread, which means that it's different thread and the different data streams. So actually, I also mentioned that GPU works like the SIMD architecture, like the single instruction multiple thread. But GPU supports the simple execution model, so which means that GPU can execute the many concurrent threads, which means that a large amount of threads can be executed in parallel. Okay, so but this model is like the rather like parallelism. If each thread executes independently, then it's not efficient. So I also mentioned that in order to handle the large amount of data in parallel, the SIMD architecture is more efficient than the other multi-core model. So GPU also has employs the SIMD architecture, but GPU also needs to support the SIMT. Okay, so GPU groups the multiple thread and 32 thread, and then this 32 thread is included in the same CPA. Because I mentioned that CPA is the thread block. Okay? So you know the GPU generates the multiple CPAs or multiple thread blocks from the same kernel. So which means that each thread, the threads within a word, share the same instruction strings, the same instruction code. And then actually, especially in the word, this word shares the same program counter. Okay. So it's like this. So GPU is the general purpose processor, like the CPU. So which means that when an instruction, the kernel codes are compiled, then GPU compiler generates the multiple instructions from the single kernel, like the add, sort, and load, and store, like this. And then these kernel codes, the instructions are stored in the main memory, right? CPU's device memory. Then what does that mean? The program counter is the same. So if the program counter is pointing the add, then add every thread, the thread, you know, the same word shares the same instruction, like add, blah, blah, blah. Also, it's the independent thread. So which means that the GPU has also support the independent registers. So which means that there are multiple threads, and then each thread also has its own registers, like the R1, R2, R3. Also, each thread, the different thread in the world also has the different registers like R1, R2, R3. So it's the same, R1, R3. So the different instruction and the different registers, but these instructions can be executed concurrently, which is the in parallel. So think like this. So instructions are the same. So these instructions because require the same execution engine, and then also same execution model. Like it requires the addition, and then these threads require different data. from the different register file space. Okay, so what is required? So there are different registers, and then but the instructions the same. So it can work like SIMD. So how? If the required operands are the source register data. If these required operands are collected from register file, and then these operands are assigned to each thread, then each thread can have some operand, the required operand. Okay, so storage threads may have the required operand, but the data are different, and then threads can be executed in parallel. So this is the SIMD model, right? So even though GPU supports the SIMD, single instruction multiple thread, but GPU works like the SIMD because the register data, because register data is collected from the large register field, large register file, and then this collected data is provided to the execution lane, the execution, like how can you say, like the execution pipeline, and then these data and instructions are provided to the streaming processor. Is called the CUDA core. So CUDA core, there are multiple CUDA cores. So multiple CUDA cores can execute the multiple instructions. So the instruction is the same as I mentioned. And then the instructions are handled the different data. So this is the work. Okay. So that's why I said that the SM, the stream multiprocessor, execute work. Okay. So actually the work is the hardware unit. It's not revealed to the software engineers. Everyone knows that. So if you are interested in GPU architecture or GPU programming, the software engineer also knows that a single work can include directed threads. Okay, that's why when our threads are organized in a CPA, then usually the thread has the number of threads is the multiple of 32 usually, but you can use any number actually. So actually no, but so this work is the hardware unit, and then actually the GPU executes the work, a single work every clock. Okay, that is the GPU's execution model. So in a CPU can execute an instruction every clock, right? So an instruction is fetched from the instruction cache, and then this instruction is also included in the instruction fetch queue, and then this instruction is decoded and then dispatched to the execution unit. Right? That is the CPU's execution model. Also, we learned the previous classes, but GPU is different. GPU's execution model is the SIMD execution model. So which means that GPU can execute the single instruction multiple data. So in order to support this SIMD execution model from SIMT, then GPU groups the multiple thread into a work, but the thread in the work share the same program counter. So GPU's scheduler, it's called the work scheduler. GPU work scheduler schedules the ready work to the SIMD execution engine. Okay, so that is the work execution model. So, which means that GPU can run multiple works, right? GPU's stream multiprocessor has also support the multi-threading, right? The multi-threading for multiple works. So what is the multi-threading? We also learned about the multi-threading in the previous classes. So multi-threading means that in order to avoid the waste of clock cycles by data dependencies, multi-threading can perform context switching among multiple threads, right? So it's like this. The CPU and then the GPU. GPU can execute the instruction, but GPU can execute the work. And then CPU multi-threading, GPU can select multiple instructions from multiple threads. But the GPU can select works from multiple, the work for execution from multiple works. Okay. So if you see the homework assignment number 1, then you are requested to get some information like the number of maximum works per SM. So which means that SM can include the multiple works, and then the recent architecture, like I believe it's Ampere. The Ampere can execute the up to 32 works concurrently. So which means that this is the single SM, and the single SM has the multiple works. The works number 0, works number 1, 2, blah blah blah. And then in order to execute this work, and there is the work scheduler here. The work scheduler select the work which will be executed by GPU's SIMD execution engine. Okay, that's how the GPU executes the work. So I'll explain about the work scheduler later. So let's compare the SIMD, but I also mentioned that GPU supports the SIMT model. So let's compare the SIMD and SIMT. So SIMD means the SIMD, so you can think like, you can understand like that. The SIMD is just to handle the vector data, vector type data. So if you see this SIMD instruction, you can find that EAD is the vector type load, EAD, and then store, the vector type store. So it means that in the CPU's SIMD engine, the CPU has the SIM vector register file, the vector register file, and then the actually SIMD instructions read data from the vector register file. So the vector has the multiple element with this multiple element, then SIMD can execute these vector instructions using vector registers. And then this is SIMD model. But SIMT is different. Then SIMT can execute the instruction. But there are many instructions. And then these instructions are generated from the single kernel code. So this is the single SIMT model. So actually, the programmers think that with the SIMT execution model, then I can execute the multiple instructions or multiple thread concurrently, and then the multiple threads can be executed independently. But how about the SIMD? In order to use the SIMD model, so we need to use the vector type registers. And then, actually these are optimized by compilers, not the programmers, but the compiler need to decide which part of code can be benefit from the SIMD execution engine. Okay, so actually compiler select decide which SIMD instructions are used for some part of the code. For SIMT, then programmer just decide how many threads are generated from the single kernel. Okay, and then this thread execute the same kernel code, and then actually the programmer thinks of the generated thread can be executed independently, concurrently. Okay. Okay. So as I mentioned in this slide, I think the advantage is that the advantages of a SIMT model is with the SIMT we can create each thread separately. So like it's a multi-core execution model, like the CPU, right? But it's just an illusion. Okay. So actually inside of the GPU, multiple instructions are executed like SIMT. Okay, but it's illusion. The programmers, actually software engineers, think that there are multiple threads. That's why NVIDIA advertised that CPUs can execute thousands of threads concurrently. But the Intel Xeon can only execute the 60s or 60s concurrent thread. So you can just compare 1000 or 60. So they think that they advertise that NVIDIA GPU is better than CPU, but it's not true. Right? So it's like BMD. It's just an illusion. Okay. So you can software engineer thinks that these threads can be executed separately, but it's not true. So then it's a feature of the CP. Each thread has its own register file set. Okay, what does that mean? This is thread number 0, thread number 1. Thread number 0 has its own register file R1, R2, maybe 255. Also, the different thread number 1 also has its own register sets like R1, R2, R1, 255, something like that. But as I explained in the SIMD model just handles the vector type data like the B1 and B2. Actually, B1 and B2 has the multiple elements like E0, E1, or E63 like this. So multiple elements. Then so it's different. So SIMD needs to use the vector type register. But in a SIMT model, each thread has its own register file set. Okay, and these registers are separately managed. Okay, and then so actually the thread it works flexibly, so which means that it supports the SIMT model supports the divergent execution path. So what does that mean? What is the divergent execution path? So which means it supports the branch. Okay. So like the CPU, so it's the feature of the CPU model. So CPU actually supports the branch instructions very it's not efficient. So with GPU supports the very diverse execution paths in our applications. So which means that in order to support these branch instructions efficiently, the CPU applies the architectural ideas such as the speculative execution or prediction. But actually, GPU does not have any speculative execution or prediction, but GPU supports branch instruction. So what does that mean? So if we have the branch instruction, the condition of this branch instruction is determined in runtime. Okay, so and then based on the condition of the branch, then the execution path is diverse. So based on the true and false of the branch, then we can execute this path of the instruction, or we can execute another path of the instruction. SIMT supports this divergent execution. Okay, And then I will explain how the SIMD can support this diagonal execution later. And this is the SIMD model. So, in the figure, we can compare SIMD like this. So, as I explained, this is the SIMD model. So, there can be multiple execution engines like the array processors. So, with the multiple execution engines, there are multiple operands, the method type operands, and then using the multiple execution engine, the multiple elements in the vector registers can be executed concurrently. That is the SIMD execution model. For SIMT, so it looks like the multiple threads can be executed separately by CUDA core, separated CUDA core. But what is different? It's actually the same. So in the SIMD model, so you can find the multiple execution engines like OP. But what is different? In the SIMD model, we can find the multiple CUDA cores. Okay. And then actually, in the GPU, using this multiple CUDA cores, the multiple threads are provided to the multiple CUDA cores. But these threads share the same PC, and it's the same instruction. And then actually, so this separated thread also share use the separated register files like this. But it is a thread. But as you can see, the execution model is similar, but we can say that in a safety model, simply the threads are separated. Okay. Okay, so let's dive into the inside of the stream multiprocessor right here. So we will first learn about this architecture of the stream multiprocessor. So if you see this figure, then you can find some multiple components like the instruction fetch, scope, work scheduler, and then some private caches. Okay, so then let's see how this stream. Let's see the architecture of the streaming multiprocessor. Okay, so let's see this figure. So this is the actually Fermi architecture. So I will explain based on the Fermi, but because when a GPGPU SIM was firstly developed, they are developed based on the Fermi architecture. So now they announced the new version of the GPGPU SIM, like the GPGPU SIM 4, but the original GPGPU SIM was developed based on the Fermi architecture. So let's see this figure. So I hope you can understand. The basic execution model and the basic architecture with GPU. Okay. So this is the hardware, it's not software. So I hope you can have the hardware perspective view, of the hardware engineer, have to understand the GPU architecture, not software. Okay. So as I mentioned, the GPU has the multiple cores. Right? So and this core is called the CUDA core by NVIDIA. And also it's called the streaming processors. Okay, it's called the SP. Okay, and then also NVIDIA GPU has the special function unit and special function. So there are multiple special function units. But this special function units supports the special functions such as the sine, cosine, tangent, or square root, something like that. So in the CPU, actually the size of the special function unit larger than the stream multiprocessor. So also the latency is higher. So because the special function unit is more expensive, the hardware architecture is more complex than the streaming processor. Actually, the number of SFU, the special function unit, is smaller than the number of CUDA code, number of SPs. Also, GPU has the load store unit. I will explain about the load store unit in the next class, because GPU also has its own load store unit architecture, which is now to support the warp execution. Okay, so if you see that this streaming multiprocessor architecture, then you can find there are multiple SP streaming processors. Actually, in this figure, there are 32 SPs, as I explained in the Fermi. The frequency of the SP is the double of the clock frequency of the SM. So that's why each warp is assigned to the 6 SP, but it's like there are 32 SPs. Okay, because the clock frequency of is SP core is double of the clock frequency of SM. So, and then there are 2 warp schedulers, okay, not SM. And then this warp scheduler issue warps, the ready warps. What does it mean? Ready means that. So this warp shares the same instruction like F, R1, R2, R3, and then ready means that the required operands are ready. So this is these are instructions. So which means that the instructions can be executed if the required operands are ready in the processor, right? So there are multiple warp schedulers, and then which means that there are multiple warps. Okay. In the Fermi architecture supports up to 48 warps per SM. So which means that a single SM can execute the 48 warps concurrently. So these 48 warps can be launched SM at the same time. So then how can SM schedule these multiple warps? So actually, if the warps are launched in SM, when I explain about the GPU execution model, the CTA, the thread blocks are assigned to the SM, and then the CTA has the multiple thread, so the thread, and then among these threads, 32 threads are selected. Okay, 32 threads are selected, and these 32 threads are grouped into a warp. But as I mentioned, a single CTA can have 100 of threads, which means that from a single CTA, multiple warps can be generated, right? But in a warp, the number of threads is fixed as the 32. Okay, this is the hardware, not software. So, for example, if a single CTA has 128 threads, then how many warps are generated? 4 warps are generated from this single CTA. Okay. Also, in the Fermi architecture, a single SM can support up to 6 CTAs. Okay, so which means that 6 CTAs can be launched at the same time in this single SM. And then this number is given by GPU generation. Okay. So what does that mean? If a single CTA has the 128 thread, and then if there are 6 CTA, then these CTAs will generate 24 warps. Right? Multiplication. Okay. The 4 warps per CTA, if there are 6 CTAs, and then these multiple CTAs will generate 24 warps. Okay. So, and then in this SM, so there are 2 warp schedulers. So, which means that some half of warp, like the warp number 0 to 11, is assigned to the warp scheduler number 1, and then the warp number 12 to 23 is assigned to the warp scheduler number 1. Okay, number 0 and number 1. So generated warps are assigned to the multiple warp schedulers, right? And each thread it's called the SYNC lane. Actually, each thread in a single warp is allocated to the each SPs. Okay, so which means that if we see the inside of the warp, so we can write the thread number. This is the warp. And up here, oh, this is the thread number 0, and then thread number 1, thread number 2, and then thread number 31. There are 32 threads. And then SP number 0 is connected to the thread number 0 of the warp. And also SP number 1 is connected to the thread number 1 in the warp. SP number 31 connected to the thread number 31. So which means that when a warp is scheduled, each thread in a warp is assigned to the corresponding streaming processors. Like this. The separately assigned to the streaming processors. Okay, and then if this instruction is the add R1, R2, R3, and then these instructions are executed in parallel. Okay, then how these warps are assigned? So I explained that in a GPU works like the multi-threading. So this is the multi-threading of the multiple warps. Also, GPU supports the fine-grained multi-threading. So we also learned about the fine-grained multi-threading in the previous class. So what does that mean? This is a warp pool. Okay, it's a warp pool. So it's because there are 2 warp schedulers, there are 2 warp pools, like warp pool 0 and the warp pool 1. So actually warp scheduler select the ready warp from warp pool. Okay. So for example, in this example, the warp pool 0 has the warp number 0 to 11, right? And the warp pool number 1 has the warp number 12 to 23. And then we can find any ready warps from this pool. If there are some ready warp, then warp scheduler select the ready warp from or ready warp from this target warp pool. So for example, in this example, so we have 0, 1, 2, 3 we have this warp pool has the warp number 0 to 11, and then let us assume that in this warp pool the warp number 0 and then 7 and 11 are available. So which means that register the operands, the required operands for these warps are ready. Then warp scheduler selector is from is ready warp number 0, 7, 11. Then select the one of warp from the ready warps by the warp scheduling algorithm. So for example, if the warp scheduler select the already warp number 0, then other warps will not be executed. So it's a kind of fairness problem. So we can also apply some warp scheduling algorithm for improving the performance of GPU in syllabus processor. So, but by based on by the specific warp scheduling algorithm, a warp scheduler select the a warp from the ready warps. Okay? So in this case, we can select the 0 by some priority. So if 7 has the higher priority, the warp scheduler will select the 7 from the ready warp. Okay. And then if warp is selected and this warp is issued to this execution unit and SPs to the core, and then this warp will execute instruction. Okay. And then what is fine-grained multi-threading? So let us assume that in this example, warp 0, 7, 11 is a ready warp, and then warp scheduler select the warp number 0, and then warp execute this warp number 0 to the SPs. So what will happen? Then this 0 is being executed. Then to remember that GPU structure is very simple. So GPU does not have any data holding unit, right? GPU does not have any data holding unit. So data cannot be holding. So for example, if this is warp 0 executed at R1, R2, R3, then by the latency of the instruction, this warp will take some cycles, like let us will take 5 cycles for add instruction. Okay, so what does that mean? While warp 0 is being executed, warp 0 cannot be executed again because of the latency of the SP. So in this example, then in the next cycle, after the warp 0 is issued, in the next cycle, then warp scheduler also searches for the ready warps from the warp 2, and then warp scheduler finds the warp number 7 and the warp number 11 is ready, and then warp 0 is not ready because it is already executed and it's being executed. So in this case, warp scheduler select the warp number 7. Okay, that's fine-grained multi-threading, right? From the multiple warps, warp scheduler select the ready warps. Okay, then GPU performs the quick context switch. So what is the context switch? In the multi-threading, the executed thread are changed. This is called the context switch. GPU support the very fast context switch. So in order to support the multi-threading, what is required? We require multiple register file set. Actually, GPU has the very large register file. It is now the model GPU has the 128 kilobytes of a register file per SM, which is very large, right? It's larger than actual cache, error cache. So not support the multiple thread, passive thread execution, passive parallel thread execution, and so not support the very fast context switch. GPU also has a set of GPU has very large register file, and they're using this large register file, and then GPU can execute the default warps quickly if the target warp is not ready. So it means that in the next cycle, in this example, GPU warp schedule is warp number 7. Then GPU will execute this warp. So this is the best context switch. Then using this context switch, GPU hide the latency of this add instruction, right? So even so, just remember that GPU does not have any data formatting, does not support any data formatting. Then how can GPU hide the data latency of the execution unit? GPU now to hide the latency of the execution unit, GPU support quick context switch like the fine-grained multithreading. Then GPU select the value warp from the warp pool. Okay, that is the idea of GPU that can hide its latency of the execution unit. The problem is that if the latency is so long, so actually, so I mentioned that Fermi architecture can support up to 48 warps, so which means that each warp scheduler can have up to 24 warps, right? 24 warps. So in theoretically, GPU, this warp scheduler can hide up to 24 clock latency, right? Clock cycle. Because so if all warps are ready, and then they predict this warp is a very long that execute some instruction which have a very low latency. Then if you can wait until 20 cycles, okay, then if you can come back to the 1.0, then execute. So because it's a theoretically the GPUs can hide tens of cycles, the latency of tens of cycles. What's the problem? Load instruction. So someone think that with this fine-grained multithreading, GPU can hide the latency of execution unit effectively. So it's someone think that GPU does not have any data dependency problem because of this fine-grained multithreading. So it can be true because if the latency of a single instruction is around less than 24 cycles per minute, then it's true. But if the latency of formal instruction is higher than the longer than the 24 cycles, then GPUs cannot hide this latency. Okay. So usually the load instruction, like the memory instruction is executed. And then if the data is fetched from the main memory cache, the cache is very fast. But if the data is fetched from the main memory, then it will take 100 cycles. Then this memory latency cannot be hidden by this warp level multithread. Okay. So sometimes the latency, like some memory instruction, the latency from memory instruction and error with GPU performance. But usually the latency of the other execution unit, it can be effectively hidden by multiple works. Understand how GPUs are executed? So now GPU was firstly developed with some researchers focused on the actually box given algorithm. So I also mentioned that we can apply the different work scheduling, which means that we can set the different priorities for the value ones. So and effectively, not effectively hide the latencies of GPU instruction. We can also apply the different type of work scheduling. Okay. So I also explain about the warps and the warp schedulers. Okay. So this figure shows compare the GPU architecture of the stream multiprocessor architecture and the out of the process architecture of the CPU. I repeatedly explain this. So I hope you can distinguish the different architecture of the CPU and GPU. Also, you can find the scoreboard here. GPU has the scoreboard. So what is the scoreboard? So we use scoreboard for checking the ready register. Okay. So actually with using the GPU with the scoreboard, GPU detect the low hazard and then wow hazard. Okay. So if we just check the destination register, then we can check the wow hazard in the scoreboard. And if we just check the source registers, then we can check the low hazard. The scoreboard checks just the availability of target registers. Okay. And then using the scoreboard, if the all target registers like the destination register and then source registers are ready, then work scheduler think that this work is ready, and work scheduler can schedule this target one. Okay, using the scoreboard, GPU can check the readiness of the work. So which means that GPU, in the Fermi architecture, a single SM supports up to 48 works, so which means that the GPU also has the Fermi architecture, a single SM has 48 scoreboards. Okay. Okay. Then let's see how this GPU's core works. Let's see how GPU's core works. So as I mentioned, the GPU supports the SIM-T, but I mentioned that the SIM-D is more efficient than the VIM-D model. So GPU work, the execution unit of the GPU works like the SIM-D. So this is the feature of the GPU core. GPU core has the SIM-T front end, and then GPU core has the SM. The stream multiprocessor has the SIM-D backend. What is the front end and the backend? In the Thomas algorithm, so we also learned about the front end and backend. So backend is this part, okay, like the execution unit, and then load store unit, execution unit, and issue queues, and write back logic. So this is the backend part of the Thomas CPU, and then we can say that the register file and decoding instruction fetch is the front end of the CPU. So it's the same to the GPU. If we mention the front end, so it means the instruction fetch and the instruction decoding and the warp scheduling. So that is the front end. So GPU supports the SIM-T high front end. So because GPU needs to support the SIM-T model, but the backend, the execution unit, and then the write back logic and the load store unit, the backend works like the SIM-D. Just remember, the SIMD front end, then SIMD back end. And then as I mentioned, GPU supports the fine grained multiple between warps, also among warps. Okay. So actually, as I mentioned, the GPUs developed by NVIDIA, the commodity company. So actually, NVIDIA or AMD do not reveal the GPU architecture properly. But we can study the GPU architecture using simulator. So I will explain the architecture of the SM based on the GPU scene. Okay, so this figure is the figure of the GPU scene. So as I mentioned, the GPU has the SIMD front end. The SIMD front end supports the batch, decode, and scheduling. Also, you can find the branch here because the GPU has its unique branch execution model. Also, and then the SIMD front end just select the warp. Okay, the warps. The SIMD front end schedule the ready warp to the SIMD backend. So, as I mentioned, the GPU has the SIMD-like data path, like multiple SPs, and then load store unit, and then special function unit. And recently, the GPU also has the tensor cores, okay, to support the matrix operation. And then GPU has the large register file. This is the one large register file, but like the 128 kilobyte. Then, actually, I said that the registers are separately assigned to the thread. So, also the number of thread per thread, number of registers per thread can change by applications. So which means that some applications, some corners, a corner A generates some thread, multiple thread, and then for this corner A, this thread can use the 10 registers. But corner B also generates some thread. This thread can use 64 registers. Okay. So it's true that there are maximum number of registers per thread, but GPU compilers can generate different number of registers that will be assigned to a single thread. So which means that like the register alias table of the out-of-order processor. So what is the register alias table? So the modern out-of-order processor has the large physical registers, but this large physical register just support the fixed number of architectural registers. But physical register is large, and number of architectural registers is small. So in order to support the large physical register, the out-of-order processor has the register alias table. So which means that map is architectural register to a certain location of the physical register. So like the register alias table of technique of the CPU domain, GPU has the very large physical register file, and then actually each register number of the thread is dynamically mapped to the location of this physical register file. I said it's dynamically, but when the kernel is launched, the location of the register file is decided, and then the address address of this register file is mapped to the register alias table of the GPU. Okay. So just to remember that GPU has the very large one register file. Then each register file can be dynamically maps the location of this particular register file. So actually, in order to support this operation, GPU has the operand collector. So because the location of these registers are dynamically decided by compilers, then in order to execute some instruction like add R1, R2, R3, actually the address of these registers are different. It's also same to the out-of-order processor because the address of the register number of the physical register number is different from the architectural register number. GPU is the same, but because this is the one large register file, these operands, so these data need to be read from this register file. It's collected. So it's larger than the cache. Okay, so how can we access the cache as right? We can access cache with the address, and then if the address is given, then we can get the data. It's the same to the GPU, the very large register file. The address of this register file is different. It's decided by compiler. So when in order to execute this instruction using the data from register file, the data should be collected from the register file. So this unit is called the operand collector. There is OC is here, and then using the OC provides the register data from the register file, and then provide the data to the simply data path. Okay. Also, GPU has this memory subsystem like cache. GPU actually supports the different spaces, different memory spaces, like the texture space, local space, constant space. So, in order to support the multiple spaces, GPU has the multiple private caches, like the data cache, and then texture cache, and constant cache. Okay, and then this is the memory system. Then this memory system is connected to the low-level memory partition, such as the L2, and then interconnection network. So this is the GPU simply code. And then this is some detailed structure of the SIMT. Actually, this, as I mentioned, this is provided by GPU. Okay. So so this is the SIMT front end, and this is indeed backend. Actually, the SIMT backend is rather simple. It's simple because actually the SIMT, the architecture of the SIMT processor is simple, but the front end is a little bit complex. But it's simpler than the out-of-order processor. Okay, so there is a batch engine here, and the batch engine with the instruction to the instruction cache. And then I said that the GPU has the multiple works. Okay, so which means that there are multiple works here. Okay, multiple works has its own instruction buffer. It's like the instruction batch queue, but there are multiple works. The multiple works has its own instruction buffer. So, and then also I mentioned that using the scoreboard, warp scheduler is the availableness, the readiness of the warp. So actually there is a ready bit, the warp to, then if from the ready warp, the warp scheduler select the warp to be executed. So it's an issue engine. And then also GPU has the CMT stack. So CMT stack is required for supporting branch instruction. So I will explain later, but in order to support the divergent execution path by branch instruction, warp has the execution mask for each thread. For example, so there are multiple threads in a warp here, right, 0 to 31, and then warp decide which thread will be really executed by this backend. So for example, this execution mask is set as the 1, then which means that the corresponding threads are executed. But if the mask is set as 0, then the threads are not executed. Okay, so this mask is called the active mask in GPU scene. And then using this active mask, the GPU supports the divergent execution. So this active mask is determined by this step. Okay, I also explain about the synthesis step. So the synthesis step provides the active mask to the warp, and then using this warp instruction, and then also as I mentioned, there is the operand collector. Operand collector collects the operand from the register file, and then using this active mask and then warp execution model and threads in the warp are executed by CUDA core and SPs. So it's called the AAU in the GPU scene. But these are SPs. Also, there is the load store unit. It's a single data path. And then there is also right band logic. So the right band is, if the execution is done and the result is written back to the register file, so it's performed by operand collector. The operand collector is the gateway to the register file. So this is how the GPU works. So it's actually this is the architecture. So this is the behavior model of the GPU. Okay. Okay. So and then I will. So let's take a 10-minute break, and then after that I will explain about the detailed architecture of each component. Okay. So any question? Okay. So let's take a 10-minute break. Okay. Let's resume the class. So actually, in GPU architecture, important part is the warp. So please understand how warp thread execute the multiple thread, CD-like pattern. So also you can understand the GPU architecture, the CMT front end and the CMD backend. Actually, the CMD backend is the same code, but in order to support the CMT execution model, GPU's CMT front end is a little bit tricky to understand. But good thing is that GPU architecture is simpler than the modern CPU architecture. The power efficiency. The GPU is the power hungry device, everyone knows that. But actually, the CPU is more power efficient than the CPU. So we can measure the power efficiency like the number of operation per function of the power, but this number, this metric is higher for GPU. Okay, it is because the GPU's architecture is simpler than CPU. Okay, also GPU does not support any speculative exchange or prediction, and then also even for data forwarding. Data forwarding is not supported. So that's why the GPU architecture is simpler than CPU. Okay, but in order to support this SIMP extension, GPU has the SIMP front end, and I hope everyone can understand about the SIMP front end of the GPU streaming multiprocessor. So actually, the SIMD data path is relatively simple. It's actually very simple. So we don't need to study about SIMD data path in the GPU architecture. But this SIMD path, SIMD front end, is a little bit tricky. So try to understand. Okay, so I will explain about the detailed component of the GPU, the SIMD front end. So as you can see, GPU has the fetch unit and the instruction buffer. So that is the component of actually the GPU SIM. So we don't know the exact architecture of the commodity GPUs, but so we just estimate that GPU looks like this. GPU has its own instruction cache, so like the CPU. So this cache, this is the error cache. So when the instruction is actually the instruction is fetched from the instruction cache. Then, like the CPU, the instructions are addressed by program counter, right? So as I mentioned, the warp has its own PC because the program, the thread and the warp share the same program counter. So which means that the warp has its own PC. Okay, PC here, warp. And then using this PC, the program counter, the warp access the instruction cache. So, but there are multiple warps, right? So there are multiple warps. So there can be multiple program counter which will access the instruction cache. So actually, we can use the simple architecture like the multiplexer. So which means that the instructions are fetched from the instruction cache to the separated instruction buffer, the round robin cache. The cache operation is the same to the cache of the GPU. So which means that the cache miss occurs, then the cache miss is handled by instruction cache, and the instruction data is requested to the lower level cache. It's the add to cache. And then let's see the instruction buffer. So this is the instruction buffer. So when the instruction is fetched from the instruction cache, first remember that this is the GPU model. So the instruction is fetched, then instruction is incubate the instruction buffer of each warp. So which means that each warp has its own instruction buffer per warp. So it's very simple. So actually this instruction buffer per warp just has the instructions, the decoded instructions, and then the valid bit. So we need to check the validness of the affected instruction. Also, there is the ready bit. So this ready bit is checked by score, and that's it. And the instruction buffer also, there can be multiple entries in the instruction buffer. Then the instruction buffer, and there is the pointer, and this pointer pointing the instruction which will be executed by warps. Okay, so it's a round robin queue. around the queue. So actually the pointer is changed and then if a warp points the instruction, the entry, instruction buffer, then this instruction will be issued. But when we need to check the readiness and then validness of the instruction buffer. So actually, this is very simple. So there are multiple warps and then multiple warps. That's the instructions from the instruction hash. And then the next instruction is including the instruction buffer. Then instruction buffer has the valid bit and then readiness bit. Then this readiness is kept by its codeholder. So when the warp is scheduled, which means the warp is issued to the simply backend, then the instructions are issued from the instruction buffer of each warp. So issuance. So I already explained about the valid bit and then readiness bit of the instruction buffer, and then issuance. So actually, I already explained about the warp schedulers. And then multiple warps are assigned to a certain warp scheduler. For example, warp number 0 to 11. Actually, in the GPGPU scene, in the Fermi architecture, there are two warp schedulers per SM. The Fermi has the odd and even scheduler, so which means that the warp of the other warps are scheduled to the odd scheduler, even warps scheduled to the even scheduler. Okay, and then warp scheduler checks the readiness of the multiple warps from the warp pool. And then if the warps are ready, so you can the warp scheduler select the ready warps from the warp pool, and then based among these ready warp scheduler select the one warp which will be issued to the backend. And then, as I mentioned, we can use some different scheduling algorithms. So basically, we can think the round robin algorithm. So the priority. So actually, when a ready warp is selected from the warp pool, then based on the priority, then the scheduler select the warp which will be executed. So we can change the priority of the warp in the round robin fashion. So which means so round robin fashion means that this is the warp number, then we can select the highest priority with the round robin fashion. 0 is selected and the 1 is selected, blah, blah, blah. But so actually, this round robin warp scheduling may not be efficient for hiding the latencies of some load instructions, so long the instructions which have long latencies. So sometimes, actually, the researchers also focused on the warp scheduling algorithm. So GPGPU supports the actually three different algorithms, like round robin and then GPO, then two-level GPO algorithm and two-level algorithm. Okay, so actually actually two-level algorithms are developed for hiding the low latency of the memories. Okay, but so actually in the GPGPU scene, we can change this warp scheduling algorithm from LRI, the round robin, then GTU and then two whether, and then also we can compare the performance of the scheduling algorithm. Okay. And then scoreboard. So scoreboard check the readiness of the work, and then as I mentioned, the scoreboard check the low hazard and the wow hazard. Okay. So if the low hazard and wow hazard are effective, then it means that the scoreboard this work is not ready for issuance. So for example, at R1, R2, R3, and then at another and so R4, R1, R5. So we can easily check the data dependency between these two instructions. So we will just check the data dependency. So which means that if this register does not have any fixed value, which means that the result for this current register is being executed, and scoreboard just check the status of this register. Okay, and then if this register is not ready, then sub instruction cannot execute this instruction. Actually, it's a work. So scoreboard check the readiness of the registers, and then scoreboard check the readiness of the certain work. And its algorithm is actually very simple because the GPU is the in order execution. GPU support only in order execution. The compilation can be out of order, but the execution order is the in order. Okay, that's why the scoreboard of the GPU is very simple. So, like the add R1, R2, R3. So in this example, this add instruction has got two source registers and one destination register, and then scoreboard check the status of these all registers. Okay, so you have to check the low header, okay, low header. Then scoreboard check the status of the source registers R2 and R3, right? Then if the R2 is ready, then it's ready, and R2 is ready, then work can execute this instruction, right? But if R2 is not ready, like 0, the status state is 0, and or R3 is not ready, then this add work cannot execute this add instruction, right? So check the readiness of the source registers. Then by doing this, the scoreboard check the low header, and then this is just it's not ready. The scoreboard check that it's not ready. So and then also GPU check the wow header, like the add another sub. So R1, R4, R5, and this. So this is in this example, so destination register of the add and sub are the same. So if this add instruction is being executed, then R1 does not have any proper result. So in this case, simply the scoreboard check the status of the destination register, and if the destination register is not fixed, so it's being executed, then scoreboard think that the next instruction cannot be executed. It just avoid the issuance of this sub instruction. It does not check any latencies or the availability of the sub instruction. So scoreboard, actually, the scoreboard of the GPU is also very simple, right? Because the GPU does not support any data holding. Also, GPU does not support any speculative execution. That's why the scoreboard is also very simple. So, scoreboard GPU just check the readiness of source registers and then destination registers. Okay, like here. So if the destination register is not ready, so which means that this value of R1 is being executed, but it's not completed. So in this case, just avoid the execution of the sub. Okay? So by doing this, the scope with the scoreboard, then we just handle the wow hazard. The GPU just handle the wow hazard. So it's very simple. Scoreboard just check the availableness of the all registers of the GPU, i.e. of the instruction. And then if this work is ready, if all registers are ready, right? Then scoreboard check the readiness speed, set the readiness speed of the instruction buffer, and then if the readiness speed is 1, then this work can be issued. Okay, it's very simple, right? So if we see actually we will also use the GPU thing for our assignment, and so if you read some scoreboard code, then you can find it's very simple. Okay, so you just check the readiness of those registers and destination registers. Okay, so that is the front end of the GPU, the GPUSM. So we learned about the instruction fetch engine, the issuance engine, and scope. And then so I will explain about the simple step of the GPU. So much little bit. Actually, the front end, as I explained, each component of the GPU is simple. But now, so I will explain about the simple step of the GPU. The simple step just to select decide the active mask of the work. Okay, so this is the example of the simple step. So why do we need the simple step? So this is the example. So simple step is required for handling branch divergence. So this is the example. It's the example corner code. So this corner, let us assume that the work size is the 4, then which means that work execute the 4 thread concurrently. So that is an instruction. So as you can see, we can find the if else statement here. So based on this is the A, so A is actually all thread in a work will execute the A, right? Commonly, and therefore based on the condition of the B, actually this range instruction. So we need to check this condition. So actually the old thread will also execute this line, but based on the condition of a branch, then B is 10, the B can be 0, and then B 10. So what does that mean? This is work. So work can execute this instruction because this instruction can be also pointed by program counter. Also, some thread in a work can execute this line, this instruction. So based on the condition, part of the thread can execute only this instruction, and then another part of the thread can execute this thread. And then after that, this is the common statement. So after that, the thread in our work execute the same instruction. Because GPU support the CMT execution model, GPU needs to support this situation. So which means that some thread in a work execute the part of the thread, some part of the thread in a work execute some instruction, and then another part of the thread execute another instruction. Okay. So in order to support the this execution, the GPU supports the active mask. And then so actually by using active mask, if the active mask is set as 1, and then only the corresponding thread is executed right in the backend. Okay, so this is the organization of the same step. So actually you can find the active mask here, and then this is the PC, and then this is the return PC. So what does that mean? If the PC is D, then we know I explain it later. So this PC is D, then this PC is comprised at PC E. So this is the return PC. So in this case, so when this D instruction is executed, we set the active mask of this warp as the 0011 because only T3 and T1 is executed, right? And then, oops. 어쨌든 뭐 인텔도 사실 프로세서 속을 뜯어보면은 인텔이나 ARM이나 사실 똑같이 아우르고 프로세서를 하고 있는데 파워 하는 게 아무래도 인스트럭션 레벨이 인스트럭션 자체가 차이가 있어서 쉽지 않네요. 오케이. Sorry about that. Because of the power failure, my laptop was turned off. So this is the CT stack. So in order to support the CT execution, the GPU supports provide the active mask for multi-thread execution. The CT stack is organized like this: the current PC, and then this is the return PC. So and then I will explain with the example. So this is the example of the execution paths of the GPU kernel. So firstly, the A is executed, and then go to B. So you can find that in this figure. So there are divergent execution paths. Okay. So firstly, the thread 1 execute so let us suppose thread 1 is execute the execution path A, B, C, E, G, and then thread 2 execute the A, B, D, E, G. Thread 3 is also execute the same path, and then thread 4 execute the different paths like this. So problem is that actually why do we use the work? Because the CP architecture is more efficient than the linear model. But in order to support this SIMD variant of the GPU, the GPU is the warp execution model. The problem is that inside of the warp, there are multiple threads, and the multiple threads may have the different execution path like this example. So it's not a good programming practice in a GPU, but it's also possible. So actually, the warp share the common piece, and how the empty stack is. Let's see how the empty stack is organized. So this is the top of the stack. So and then RPC is the reconverged piece. This inlet the return PC. And then so this is the next PC. The empty stack has the active mask information. So when the A is executed, so you can find that when the instruction A is executed, all threads in the world execute the same instruction. So which means the active mask is the 1111. So all threads are executed. So in this case, this is the execution time. So this is the time. So when the A is executed, all threads are executed. And then let us state the B is executed. When the B is executed, so we assume that the all threads in the warp are executed. So the next PC is the B and the active mask is the L1111. Because when the all threads are executed, they convert the PC is also nothing. But when C and D are executed, we can find that when the branch instruction is executed, then we can find that some thread in this warp are executed, and another thread in this warp are executed in the different paths when the branch instruction is executed. So in this case, when the C and D are executed, then execution path is divergent. So in this case, so we update the stack, and then we know that when the C and D are executed, then we convergently at execute instruction E. So in this case, when the D and C, so that's the PC, then the converged PC becomes the E in this case, and then the active mask is determined. So which means that when the branch instruction is executed, the active masks are combined based on the condition of the branch. And then the top of the stack is pointing to this line, this entry. So when the C is executed, then we know that the active mask is 1001. So the mission is that when the warp is issued, and this warp read the active mask from the CP stack. And then the top of the stack is pointing to this entry. So active mask becomes the 1001 here, 1001. So only two threads this warp is executed. And then same. And then when this instruction is executed, then next PC becomes the E. So in this example, when this is the top of the stack, when this entry is pointed, the next PC was the C. And then C is executed. So which means that the next PC becomes the E. And then we know the next PC is the same to the convergence PC. So in this case, we already know that this path is executed. So stack pointer is moved up to this entry, and then next PC is the D. So which means this warp will execute the instruction D with the active mask of 0110. So in this example, the C executes the only two threads here, and then D executes the two threads like this. And then after the is complete the execution of instruction D, then next PC also becomes the E, right? Because it is converted at E. So the top of stack is moved up. Then the next PC is the E, then active mask becomes the 111 in this case. So and then G is the same, then stack is changed, active mask is the 1111. Okay, so that's how the empty stack works, and then how the warp with the active mask from the empty stack. So the empty stack, not to support the diverse execution path, the GPU has the empty stack, and then the empty stack managing the next PC and then active mask. And also the empty stack manage the deconverted PC. Okay. So what's the problem? The why? But even though GPU supports the same key execution model, then so which means that we can easily use the branch instruction in GPU program. But what's the problem? So if we let us assume this is the clock cycle, and then in this example, at this clock, when instruction A execute the four thread, so which means the four instructions, and two instruction. So what's the problem? Until the instruction B, the IPC for this warp, IPC for this warp is the 4. It's simply I simply calculate. But in the diverse path C and D, the IPC is the instruction for clock, becomes the 2. So what's the problem? So actually the maximum IPC by this example is the 4. We already know that. The maximum IPC is the 4, but and the execution path is diverse, and then not to support the diverse execution. The GPU, the performance of the GPU becomes the half of the maximum performance. The IPC becomes the 2. That's why the GPU supports the simple execution model, but if you want to exploit the performance of the GPU memory, then it is recommended not to use branch instruction because of the divergent execution path. Only the part of a thread in a warp is executed. Okay, that's why the performance of the GPU program is not fully utilized because of the same execution model. So that's why it is because the GPU has the same backend, or not just the same execution. These libraries in path are executed like this with the active mask. So active mask is also important. So if we check the active mask of the executed work, then we can also calculate the efficiency of the power application. If active masks are always 32, all threads are activated, then performance will be very high. But the all processing engines of the single backend are utilized. So active mask has, if active mask has a small number of ones, then performance will be low. Okay. Okay, and then I will briefly explain about the operand collector. So I explained that the GPU has the very large register file, and then actually when a warp is executed, and then I'll share the same instruction, but data are different. So obviously different. Then the register also I also explained that the registers are independently managed by thread. So actually these register values are collected from the large register file. Then operand collector collects the requested registers from the large register file. So think like this. Register file is very large, and then now to support the high throughput from the register file, GPU register file is composed of many banks, multiple banks. Okay, so if the memory component has if a memory component is composed of multiple banks, then we can utilize the memory level parallelism, right? Because bank is the independently working component in the memory system. So GPU register file is also composed of multiple banks. So, and then based on the register number, then operand collects the requested data from this register file on multiple banks, but based on some register number, then we can encounter the bank conflict. What is the bank conflict? If the request is two requests are given to the same bank, then this bank cannot service these multiple requests. Which means that the first clock is requested serviced, the next clock then this request is serviced. That is the bank conflict. Now, what is the problem of bank conflict? The performance. Because the cycle is wasted, the performance is derailed. So actually, though, we cannot control the bank conflict of the register file. But the GPU register file, as I mentioned, the GPU register files composed of multiple banks, and then also the registers are assigned these multiple banks efficiently. Okay. So, for example, in this example, this instruction does not encounter bank conflict, but this instruction encounters the bank conflict. So this is the architecture of the operand collector. Actually, this figure is I copied this figure from the NVIDIA patent. NVIDIA does not reveal their architecture publicly. We can find the clue of operand collector in the NVIDIA patent. So there are multiple banks, and then so this is the crossbar, the interconnection network to the operand collector logic. Okay, and then also it is arbiter. So this arbiter is very similar to the register layers table in the CPU. Okay. It's always. Okay. So from the multiple banks, and then through the crossbar, then the red data is connected to the operand collecting unit. As you can see, you can find the work number here. This is the instruction, and so you can find the registers here. Okay, and then the work has the 32 thread. Then which means that for the same register, this same register requires the 32 data from the register.